Hi everyone, and I'm back with paper 2 for physics, January 2021. So let's get started. I'm going to try to do all 6 questions in one go. I have them pre-answered, and here we go. So it says, Figure 1 shows the apparatus which is used by 2 students to carry out an experiment to determine the focal length f of a lens by using the object distance u and the image distance v. At the end of the experiment, the object distance u and the image distance v were recorded in table 1. And so if you look here, what they would have done is given you u, and then right here they would have given you the application for here. So they filled in some spaces here, and this is telling you to divide 1 by whatever number is u here. Now the number you will get here wouldn't be 5, it will be 0.05. So they want you to put the whole number here, and then you would say multiply by 10 to the negative 2, because if you multiply 5 times 10 to the negative 2, you will get 0.05. Okay, so that's what they want you to do, is put it like with a whole number in front and decimal place at the back. And here we have 5. You should get 5, 2.9, and 1.8. And then in the next column, we have V. All the V's are given. And so you're supposed to divide 1 by the given value for V. And again, it wouldn't be 1.7. You will get 0.017. 0.017. Yes, if you divide it, no, you put 1 divided by 60 in your calculator, yes, you get 0.0166666666. So you have to round up, because if you also look at this, you would see here that all of the answers that they have here, all the values they have here are 1 decimal place. So you need to also follow that. Don't write this. Let's see here. Don't write. Let's go here. Don't write this where you have, don't write just 5. Don't put 5. No, they put 1 decimal place for a reason, and so you should follow the modes. They keep within that. Okay, so if you have 5.0, 1.7, 2.9, 4.1, 1.8, you're well on your way, there's. Okay, so moving on, I'm going to clean this off. We're going to move on. It says complete table 1 by calculating the missing values. That should give you 6 points. And it says on figure 2 on page 5, plot a graph of 1 over u against 1 over v using 2 centimeters to represent 1 times 10 to the negative 2 per centimeters on each axis. Okay, so we could do that. Now, I already plotted, and I'm going to show you what I did. Okay, so here we have the graph, and they told us exactly what to do. They said they want us to calibrate it at 2 centimeters each. So 1 square is 1 centimeter, so 2 squares will be 2 centimeters. So we calibrate it like that, and from on the next side you realize a range. What I mean by range is that starting from the lowest number to the largest number, I would say this has a range from 0 to 5, and this also has a range of around 0 to 5, because this went from 1.8 to 5, so I just cover it 0 to 5, and this goes 1.7 to approximately 5, so 0 to 5. So when we go over here, you realize that you have enough space. Every 2 spaces you have enough to go beyond 5, beyond the range, and it just kept going. Okay, now they said 1 over u against 1 over v. So one thing you need to do is make sure that you label your axes. Okay, and you also put in that the figure you use here will be multiplied by 10 to the negative 2 per centimeters. So that's what you need to do, and that's pretty cool. So we're good to go around here, right? And so to plot, you just look at whatever this is. When it's 1 over u, the figure is 5, and then when it's 1 over v, the figure is the figure is 1.7. Yeah, so 5 and 1.7, this is 1.5 here, 6, 7. So look over here. So yeah, so when it's 5, it is 1.7. And you go, if you don't know how to plot a graph, I have videos on that as well. So 5, that's your y-axis, come across, go down, and then you have 1.7 right here. So that would be a point, that would be a little coordinate right here. And then I plotted all of them. And if you look at it, it looks like a straight line. So the next questions are going to ask you to manipulate the graph, or are going to ask you questions based on the graph you produced from the information given in the table. So if you if you've graphed incorrectly, everything here would be based on your graph. So you have to be careful. But the good thing is that usually the markers mark how well you break down, how your understanding is, so you break down your calculation. So let's go. So it says use the graph to determine the value of v when 1 over u is 4.0 times 10 to the negative 2 per centimeter. Well, I already went ahead and drew a straight line, because usually when you have graphs in physics, you have to draw your best fit line, and then if you have a curve, you draw your best fit curve. So what I did is I drew my best fit line, and it's pretty much a straight line. Then I went and I found where 4.0 times 10 to the negative 2 per centimeters was located on the y-axis, which represents 1 over u. And then I found the coordinate that corresponds to where it touches the line. So basically we did an extrapolation. So at 4.0 times 10 to the negative 2, you drag it across here until you touch the line, and you bring it down. Okay, and I got 2.7 times 10 to the negative 2. But the catch is that is the 2.7. So it says when 1 over u is 4.0 times 10 to the negative 2 per centimeters, 1 over v is 2.7 times 10 to the negative 2 centimeters, but they asked for v. So to solve for v, you would divide 1 by the answer. It's like this: if you have 1 over v and your answer is a, which is what we have here, a, you want to solve for v, so you have to transpose, so you get v is equal to 1 over a, right? A being the 2.7, and then you get back at 37 centimeters. So that's what you have to do for this, so you have to be very careful. Now the next question asks to use the graph to determine the intercepts C1 and C2 on both axes and calculate the average value of C. So the intercepts is where the purple line, the best fit line, cross both axes. So where it crosses the y and where it crosses the x. And as you see here, it crosses the y at 6.6 times 10 to the negative 2. Okay, and then it also crosses the x at 6.6 times 10 to the negative 2. So we have the same number. So working out the average wouldn't be hard at all. You would just, what I did is make it clear that C1 was equal to 6.6 times 10 to the negative 2 per centimeters, and that C2 was equal to 6.6 times 10 to the negative 2 per centimeters. Then I showed my knowledge by saying, hence, if you want to find the average, because to calculate the average value, you have to add the two numbers and divide by 2. Since it's the same number, you don't have to do too much thinking or any calculator work, because you can get back the same number. The same answer, so it'll be 6.6 times 10 to the negative 2 per centimeters. So that's the average value of C, okay? 6.6. Okay, so they said to use the formula C equaled 1 over F to calculate the focal length F of the lens. So given that formula, you're going to have to transpose, and once you know to transpose, you could answer the question well. So when C is equal to 1 over F, then F will be equal to 1 over C. It's an easy transposition. Maybe I should stop saying easy because some people don't understand transposition. But if you want to solve for F, to get F, you want to get F in the numerator side, so you multiply each side by F. Once it's being divided, or once it's doing the dividing, you do the opposite of dividing, and you multiply both sides by F. F will cancel, and you will be left with F C equals to 1. Now you want to get rid of C. So since C is being multiplied, you do the opposite, so you divide both sides by C. Now you have F is equal to 1 over C, which is C right here. So that shouldn't be too hard to remember. But if you need help in transposition, hit me up. I will leave my contact in the description. Okay, so once you get that, you will see that F now will be equal to 1 divided by 6.6 times 10 to the negative 2 per centimeters. Okay? And what you want to do in your calculator is to make sure you have brackets around the multiplication. Otherwise, your calculator cannot think. It cannot think for you. It doesn't understand the order, so it might give you an incorrect answer. However, this is the answer you should get once you put in your brackets, and you get 15 centimeters. So F, the focal length, is equal to 15 centimeters. And that should do it for you. Alright, so the next question, the last question for question 1, it says, complete the following statement. No, personally, I don't like to give too many opinions sometimes, but I don't like questions like these without word banks. They could give a word bank with at least 10 words, and then they're giving one dash, which could hold more than one word. It's like you're trying to trick. I don't get it. Anyway, so this is what made sense to me. And if you have anything else that makes sense to you, then shoot it down in the comments below. So it says the principal focus of a concave lens is defined as the point on the principal axis from which rays originally appear to converge to the principal axis, then spreading or diverging after passing through the lens. On the exam, I would have probably only gotten point because everything else would have been a blur probably. But anyway, if you have a diverging lens, which is a concave lens, you have the principal axis, and we represent the lens as a straight line. And if you practice your ray drawings, your ray diagrams, then this should look familiar to you. If you have not, you need to really practice it, because sometimes they might bring a question where they tell you complete the ray diagram. Oh my God, you really want to be able to do this, because if you don't know how to do it, you're going to feel really bad, because ray diagrams are very easy. No calculations at all, just easy to do. So with a divergent lens, where we represent as a line, so this is a lens right here. The rays, I use 3 parallel rays, and the middle one usually runs across the principal axis. So we have the principal axis right here. And then what happens is that the rays diverge. But how they diverge so that you can get some semblance? You pull them back to some point where they seem to converge, right? When you draw them out, you're going to realize the importance of doing this. If you were to draw it without having some point of convergence here, you might get one ray going really like up like that, and another ray, the equidistance between the two will be weird. And then the ray that travels along the principal axis stays undeviated. It just goes straight, continues going straight. And this ray that goes along the principal axis will pass through a point called the optical center. Yeah. Okay, so pretty much that's how you do it. Okay, so it says state the principle of moments. So for a system that is balanced or at equilibrium, the sum of all clockwise moments is equal to the sum of all anti-clockwise moments. The next question says state another condition that is necessary for a body to be in equilibrium. So the next one is that the sum of all upward forces is equal to the sum of all downward forces. So we're in question 2 now. So there you can see that we're dealing with moments. Now then it says State the formula for the moment of a force, providing the meaning of each variable and its SI units. So it will be M equal to F times D. M represents turning moment, which has a unit of Newton meters, because force has a unit of N. That's my bad right there. It should be N. And this, well, it's newtons. So N represents newtons. N represents newtons, or Newton, and then distance, which is in meters. There's only 3 marks. Well, I shouldn't say only 3 marks, but they ask for the equation. They ask you to explain what each of them are. Just telling each one, and then they said give the SI unit, and we have your Newton meter. So you have the names of the unit, and you also have the symbols of the unit. So to cover yourself, you do this, you give the name of each, and you still name the SI units and give the symbols, just to cover yourself. Here it says this was probably the biggest. Well, it seemed hard because when I went through it with my kids, they were not talking, they were just silent. So I would think that this would have posed a bit intimidating to them. So it says, figure 3 shows a girl standing on a uniform plank, AB, of length 3 meters and weight 270 newtons. The plank rests on 2 scales that are located at position P and Q, a distance of 2 meters apart. The scales are equidistant from the ends of the plank as shown in figure 3, and the scale at P reached 354 newtons and the scale at Q reached 417 newtons. And then they give you this picture with this Asian looking girl, and then they said on figure 3, draw and label all the forces that are acting on the plank. So usually when I'm given a question like this, or when I see a question like this, I start drawing the forces right away. I don't wait. Okay, I don't wait for the question to ask me that. So these are the forces. So they told you that the scales are equidistantly placed away from the edges, meaning that means simply that it's the same distance away from each edge. Now in here they told us that the scales were 2 meters apart, so you had 1 meter left to play with, because this is the beam here is 3 meters long. So if these are equally placed away from the edge, then each of it will be 0.5 meters away from the edge. That would add up to 1. And so I put the weight here acting on the scale going up. So it's called like a reaction force. And so the downward force of the rule at P and Q are not considered because these forces are not on top of the rule, like she's on top of the rule, right? So they're placed upwards, and so this force is 354 newtons and this force is 417 newtons. Okay, so those are going upwards. Then the weight of the meter would definitely be at the center. Anytime you think about weight of something, it always acts at its center. So I know that 270 newtons will be at the center of the beam. And that's why I have this other arrow here indicating the weight of the girl should be acting from her center onto the beam because it's on top, right? So, all right, so we have all of this. Okay, now it says on figure 3, draw and label all the forces that are acting on the plank. So we have all of these, so that should give us over 2 marks. Then it says calculate the girl's weight. Now remember, the sum of all forces, all upward forces, is equal to the sum of all downward forces. Hence, if you add all the upward forces and you equal to all the downward forces, which is 270 plus xn, we could solve. So we have 354 plus 417 equal to 270 plus x. You subtract 270 from both sides, and this total will give you 771, which you see here. Subtract 270 here as well, and you will end up getting 771 minus 270, because this is going to cancel out, and that will give us x. So x will equal to 771 minus 270 newtons, and we'll get 501 newtons, which makes sense. Okay, so that is her weight. Okay, so moving on. It says, by taking moments about Q, calculate the girl's distance from the scale at Q. So if we take moments about a point, in this case Q, that would eliminate it. So we're not going to even think about the 417. I think that was there, right? So this would be an actual pivot. So just imagine this is some type of pivot, and we're just dealing with it as the force is acting towards this particular pivot, so we're ignoring it. So we're going to look at the forces here. So usually some people can't tell which force is going clockwise and which force is going anti-clockwise. I made a whole video about that, and I would tell people, put the edge of your pen at where the pivot is, and then you hold it down with your finger, and then you move the other end of the pen or pencil in the direction of the force. So if you place a pen here and put the point, you place some pressure here on the edge of the pen, and you pull down the other end in the direction of this force. You will see that this force will be going anti-clockwise, and this force will also be going anti-clockwise. So the 501 Newton and the 270 will be going anti-clockwise, whereas this force will be going clockwise, because if you move the pen in this direction, it will move up like that. So with the anti-clockwise moments, we know 501, which is the girl's weight, we're going to multiply it by the unknown distance. So we're trying to find x right here, and then we're going to add it, because all the anti-clockwise is some of the anti-clockwise moments. We need to find it, so we put all the anti-clockwise moments together. Remember, sum of anti-clockwise moments equal to sum of clockwise moments. So we have to add all the anti-clockwise moments together. So we have 501 newtons times the distance plus the other anti-clockwise moment, which is 270 newtons times 1 meter. How do I know it's 1 meter? Because in here is 2 meters, and the weight of a body always acts at its center. So you're going to be in the middle of the 2 meters. So that's going to be 1 meter away. In here is 2 between here. This is 1 meter away, as you can see here. And so we're going to work that out later. And then for the clockwise moment, now we said 354 newtons times 2 meters. So we know that the point P was 2 meters away from point Q. Okay? And so we multiply it by 2 meters. Then we just equate the two. So we said 501 newtons. This should be an x right here, because I changed it to x, because this is an x here, so I was trying to keep it uniform. So 501 newton x plus 270 newton meters equal to 708. Because this has an x, we can leave it, and then we subtract the like terms. So this is nm. So we subtract 270 newton meters from both sides. That goes, you're left back with 501 nx, 708 newton meters minus 270 newton meters. And so this will give us 501 newton x equal to 438 newton meters. Because this is like a multiplication, well, not like, this is a multiplication of 501 newtons times x. We divide both sides by 501 newtons, because we're solving for x. And we're going to realize that the newtons disappear, and we have x. Once you divide, you should get 0.87, which is correct, because if the distance between the weight of the plank and the Q, point Q, the moment Q, is 1 meter, then the girl is close to that pivot or point Q, and if she was more than 1 meter, we know would be incorrect. So it had to be less, the distance a little bit less, right? So 0.87. Yay! So that his answers. So that is question 2. I hope this helped. Let's move on to question 3. It says, define the term pressure. So pressure is due to a force acting upon unit area, where P is equal to force over area. That should give you 2 marks. Then it says, state the SI unit of pressure, pascals, in terms of its base units. And we could use this. So if we know that the unit of force is newtons, so if we have P equals to F over A, we know the the unit of force here will be newtons, and the SI unit for meters would be, for area would be meters squared. So this should give you, because this newtons per meter squared is equivalent to the pascal. So that should be fine, right? Okay, so it says, describe with the aid of a diagram how the pressure in a liquid varies with the depth of the liquid. So I would draw a bottle, and I would draw it with water inside of it, and then I would draw some holes at different levels, and I would show that when you fill this bottle up with water, the intensity of the water coming from the bottom will be much greater than the intensity in the center. And then of course the intensity at the top will be like a drizzle coming down, right? So that would be my way of showing people this, that in liquids, the greater the depth and density of a liquid, the greater the pressure it exerts on the bottom of the flask. On the other hand, pressure decreases with decreased depth and density of the liquid. So the higher up, the more pressure you're going to have down here. So pressure is greater at the bottom and less at the top. Therefore, you have less intensity with the water spouting out, and greater intensity with it shooting out down here. This is state the equation for the pressure difference between 2 points in a liquid which are a vertical distance h apart. And so you would say pressure in liquids is equal to rho g change in height. So change in pressure in liquids is equal, well, not in liquids but in fluids, because fluids could be gases and liquids, is equal to rho g delta h change in height. So delta stands for change in our difference in, and the rho is density. So rho is density, g is the gravity, and h of course is the height. Okay, usually when you work these out, you use units that are SI. So with rho you would use kilograms per cubic meter. With gravity you use newtons per kilogram, because then you're going to realize when you're canceling, the canceling would make sense. And with height, you want to always use meters, so you use SI units with rho GH. So figure 4 shows a U-tube containing 2 immiscible liquids, X and Y. And it says here, if the density of X is 1350 kilograms per cubic meter, calculate the pressure in pascals due to the liquid column AB, which is 8 centimeters long. You start listing out your variables, list out all that you have. So they're asking you about the pressure. What will be the pressure felt at this point right here? So this liquid is obviously less dense than this liquid, or more dense, I don't even know. So this is liquid X. Okay, so I don't know. It just all depends on, I can't tell because we're not in an actual glass here. I don't know which end what was placed on what. So let me take that back. All I know is that I'm asked the pressure that's felt here. I'm given the density of liquid X, right, which is 1350. I placed that, and this has SI units. The gravity was given on the next side, but I gave it in meters per second squared. You don't want to use the units of meters per second squared unless you're dealing with acceleration problems. When it comes to pressure, you want to use this because your calculation gonna look much nicer. I'm gonna show you why. You're gonna see why. So gravity is given as 10, and I put these units instead of meters per second squared. And then I had to convert the height because they gave 8 centimeters. So some people would have gone wrong if they continued with 8 centimeters and not 8 meters. You're doing a video.
But I'm looking for Annabella and she's just...
Go downstairs. You went with her. You went with her.
I went with her.
Mm-hmm. Close the door, Nish. Close the door. So if you look at this now, we could put in our numbers. So the density would be 1350 kg per cubic meter, and then we put 10 newtons per kilogram, and then we multiply by 0.08 meters. Now look how nicely the unit's gonna disappear now. Cancel, 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 and this should be a 2. So we know that our answer would have newtons per meter squared. Okay, and that is exactly what we said the units would be, the base units would be. So if you calculate now, 1350 times 10 times 0.08, you should get 1080. Now why is it better to use in newtons per kilograms? Because let's do it without that. Let's just multiply the units that they gave us, meters per second squared, and then meters. Let's start canceling now. You can start to run into problems because it's gonna look unfamiliar. You can just be like, what? This goes, and so you're gonna end up with these kind of units: kg over meters second squared. So this is the units you will end up with: kg over meters per second squared. And then you're just like, okay, this look weird, right? So that's why. And then I'm gonna show you again why you don't use it on the next slide. Okay, so now they said, hence use your answer in C1 to calculate the height h of the liquid column CD. So this is a liquid column which is dependent on where this liquid column ends. And then they say, given that the density of liquid Y is 900 kilograms per cubic meter, it says state any equations used and fully explain the reasoning in obtaining your answers. And CG here, meters per second squared. Not so much fun with that. So now we're going to use the pressure. So we know the pressure that's exerted here on this liquid is 1080, and we know the density of the liquid is 900 kilograms per meters cubed, and then we're going to use 10 newtons per kilograms, and then we're looking for h. If we stick this in, well, first we have to solve for h. So what we usually tell students is to solve first before you put in all the numbers, before you substitute the letters for numbers, because you could run into problems. So if you want to solve for h, you could divide both sides by rho and g, and there you have h. So we all know that h will be equal to pressure divided by rho and g, and so we could just stick in our numbers now. We have pressure is 1080 newtons per meter squared, and then we divide in by the rho, which is 900 kg over meter cube, and then we multiply by 10 newtons per kilogram. Again, let's just pull everything out now. So we want to see how units can play out. This is why I use newtons per kilograms again. So once you have a fraction on top, that stays the same. So let's see, newtons per meter squared. Fractions on the bottom get flipped. So we're going to have meters cubed, over kg. So So let me make this clear that this is cubed. And then we're going to flip the next fraction, which is kg over Newton. So you want to do all of that. The Newton is going to cancel out, the kilograms cancel out, and this cancel out this. So your unit is going to be meters. Let's look at it now. Suppose we were not using newtons per kilograms and we're using meters per second squared. Seconds squared will go on top meters, and then we just fill it in now. So mg cubed, mg cubed over kg, and then we have n over meter squared. Let's look at it. Let's see what units we will get now. First of all, this goes, that stays, and now we're left with these weird units here. We have Newton second squared kilograms. You're looking at this, your little young eyes, you're just like, huh? So you really want to use units that are going to, boost your confidence, because by the time you see this, you just be like, I'm getting it wrong. You're really not. It's just that you're not accustomed to seeing this kind of concoction that's happening here. So that's why I would say with pressure in liquids, I would use newtons per kilograms whenever we're doing calculation, because then I will get back the units that are favorable. So now that I know if I use these units, my answer would be meters, I go right ahead and I start calculating. So 1080 divided by an open brackets, I put 900 times 10 close brackets, and I will get 0.12 meters. So that would be my answer right here, 0.12 meters. Okay, you want in meters. Great, so good. And that was a whole 5 marks. Oh my goodness, that's a lot of marks. Okay, so now we're into section B, question 4, and it's a lot of theory in this part. And even if you didn't know how a vacuum flask work, you could have just used some background information, like what you would have learned over the years coming up from grade 6. So it says a young student has just entered secondary school. He was accustomed to having his home cooked meal warmed up at lunch in the microwave oven at his primary school. He misses this and suggests to his parents that they buy him a vacuum flask similar to the one shown in figure 5. So here we have it. The vacuum flask is equipped with a cork stopper, double wall glass vessel with silvered walls. So your brain should start ticking here. You have a vacuum, of course, because it's a vacuum glass, and a surrounding glass, a surrounding flask, and then you have 2 cork supports. Okay, so we know all the parts of the vacuum flask for this particular vacuum flask. Now it says, using the information in figure 5, explain in terms of the principles of thermal energy, another word for heat, transfer, how each of the following sections of the vacuum flask helps to keep the home cooked meal warm. Okay, so the cork stopper, first of all, think about it. The cork stopper is a poor conductor of heat, so it traps the heat inside of the flask effectively, hence very little heat is able to leave the flask. Now the vacuum, think about a vacuum. Light travels through a vacuum, right? That comes from radiation. But however, conduction and convection, they cannot occur within a vacuum because this type of heat transfer requires matter. So conduction and convection requires matter travel. Remember, there is no matter within a vacuum, so heat gets trapped within the vacuum effectively within the flask because the vacuum would not allow heat to be conducted away from the contents of the flask, from the contents of the vacuum flask. Then the double wall vessel with silvered walls. So we already started to think about silver, reflective. Okay, silvered surfaces are poor absorbers of heat. So heat gets trapped within the vacuum flask as it is reflected back to the contents of the flask. So you will get your marks for just writing things like that because it shows your understanding somewhat. Here's the next experiment. They like to bring these these heat loss experiments. So these usually deal with specific heat capacity and specific latent heat. So in an experiment to determine the specific latent heat of fusion of ice, shown in figure 6, the following results were obtained. The initial mass of the water is 120 grams, and the initial temperature of the water is 35 degrees Celsius, and the final temperature of the water, and the initial temperature of the ice is 0 degrees Celsius. The final mass of the water ends up being 140 grams, and the final temperature of the water plus the melted ice is 18 degrees Celsius. And usually I would tell people to write down their variables, but not in so many words. I would just say pick something that makes sense to you mentally. I only wrote the words down here so that you could understand what I mean by MWB. So for me, MWB would be the mass of water before ice was added. And if you minus all these wording, it'd be a simple little map for you to follow. So I have all of these things written here. I even worked out my temperature, my mass change. Mass of the ice, I worked that out, and I also worked out the temperature change. All beforehand. These are just scribbles you would make on your exam paper. So it shows you the picture here. And it says assume the container has negligible heat capacity and that there is no net heat transfer. So we basically be pretending that we're working in this perfect little system where there is no heat transfer, just so that we could do the calculations we want to do. Because if we start to take on those little things, when we start to think too hard, that's when things go out of whack, right? So it says determine the mass of the melted ice. This was the easiest question of the lot because all you had to do was subtract the mass of the water the mass of the water after the ice was added from the mass of the water before the ice was added. So I was real specific with my wording. So 140 minus 120 grams give you 20 grams. So that would be the mass of the ice, right? And you could always say the mass of ice. And so you put mass of ice so that they understand that you know what they're talking about, right? Okay, and then you put the word melted because it's a mass of melted ice. So if you want to be real specific, mass of melted ice. So you could do it like that. Then it says calculate the heat lost by the water because the water did lose heat. It went from 35 to 18 degrees. Okay, as can be seen here. So to calculate this, you say EH is equal to the mass of the water. The mass of the water is 120 grams. And then the specific heat capacity of water, I took it from the other side because they usually tell you these things at the end of the question or within the question, but they chose the end of the question. So the specific heat capacity was 4.2 joules, and I was able to keep grams because when I saw grams in here, I knew that I could use grams divided by degrees Celsius. They gave it as Kelvin, but just know you don't have to convert your temperature into Kelvin if they ever give you the Kelvin state here, because they're interchangeable in heat questions, not in gas laws, right? So you don't have to change the temperature. So we're gonna subtract 35 degrees. What I was trying to say is that they gave it with a K, and you could just put the degrees Celsius here to solve, right? You don't have to convert your degrees Celsius to Kelvins. Okay, so you find the difference between these, and you're gonna end up getting, so let's do it now, 120 times 4.2 times open bracket 35 subtract 18, and you get 8568. Okay, 8568. Now you cancel out your grams, and I always tell everybody put in your units. Always put your units in so you can see where you're going wrong. Now if I wrote this in the way that will make sense, so we said 35 minus 18, and then the degree Celsius would account for both numbers in here, then canceling it would be nice and easy, and we're left with joules because this is heat, right? The unit of heat energy is joules. So now we have 85 to 68, and we're good. Okay, then they said write an expression for the total heat gained by the ice in melting and the melted ice in warming to 18 degrees Celsius, right? Heat loss from water equal to the heat gained by the ice. That's pretty much it. So EH, water, equal to EH, ice. That's all. Now, it says, hence calculate the specific latent heat of fusion of ice. So since we know that EH water is equal to EH ice, we could transpose, and we know EH ice is equal to MLF, because with this, whereas before the water, with the water in the first instance, right, it went from point A to point B, and there was a temperature change of 35 degrees Celsius to 18 degrees Celsius, right? So that was a temperature change. Anything with a temperature change and no phase change, you're going to use MCAP. With the ice now, you went from ice to liquid. You went from solid to a liquid, right? And once you have a phase change, there'll be no temperature change, right? Right, so there'll be no temperature change between the phase change right here, okay? And so with that, with phase changes, you went from ice to liquid right here, ice to liquid. So this, because there is, it's just we're dealing with the phase change. Whenever you see the word latent, we're looking at the phase change, right? We go from, we say EH equal to MLF. So from solid to liquid, liquid to solid, that's latent heat of fusion, and we're trying to solve for that. How we solve for that? We use whatever the ice was, which was 8568 joules, and you divide by the mass of the ice, which we found to be 20 grams, and our LF would be equal to 428.4 joules per grams. 428.4 joules per grams. Okay, so that would be your answer. Okay, this is the latent heat right here. Just remember that latent heat has the same temperature, so the latent heat they're talking about is just between when the ice was changing from ice to icy water, and so there'll be no change in temperature at that point. Okay, so that's the point we're looking for right there. Okay, so now we're on to question 5. It says draw the electric fields for each of the following arrangements. So we're dealing with charged particles and charged objects. And with charged particle, when you have a negatively charged particle, the electric field lines always go towards the negative charged particle. So that's what you would do right there. You can also get fancy and start to do your diagonal lines, like a little snowflake. And these are all arrows, by the way. It's just me losing control of the mouse somewhat. So they're going towards. And then with this one, you have like charges, so they're going to repel. So easy repulsion field lines, you just draw them away from each other. But just remember that with the positive charges, the arrows go away from them. So they're really testing your understanding or your knowledge if you realize the direction of the arrows. So the direction of the arrows for positive particles are away from with electric fields, and for negative particles that come towards. So now they gave you a positive plate and negative particle, and the funny part is in the book, this is positive and these are negative and this is positive, so they did the opposite, and this was just playing with your mind, because you'll be thinking, I remember this, and then you draw your arrows wrong. Now remember, with the negative, the field lines are always going towards it, so you're going to have this coming towards here, and then here, and the positive always going away from. So this is perfect to show you how to do it. And then here and here. Okay, so this is it. So this is for 2 marks, no 6, 2, 4, 6. So if you didn't know this, oh my god, that'd have been like 0 marks out of 6. Children, students, private learners, make sure y'all study everything. Then it says here, if the number of electrons transferred from a charged rod to Earth through a wire is 4 times 10 to the 8 and the total charge transferred is 0.6 C, calculate the size of the charge on 1 electron. So I usually do relations with these things. So these are the amount of electrons here. So for this one, so with a charge of 0.64 coulombs, it transferred 4 times 10 to the 8 electrons. So what charge would transfer 1 electron? It gotta be less, because this is 4 times 10 to the 8. So this, how I would see this would be something like this. 4 times 10 to the 8 electrons over 1 electron. And then I would solve for x. So x would be equal to 0.64 coulombs over 4 times 10 to the 8. Yeah, and then you should get 0.64 divided by open brackets 4 times 10 to the 8, 1.6 times 10 to the negative 9. Yeah, 1.6 times 10 to the negative 9 electrons. Then it says calculate the current that flows through the wire if it takes 0.4 seconds for all the electrons to flow through it. So we have the time, t is 0.40 seconds, and then we have the charge, which is, the charge is 0.64 coulombs. So to find the current now, we just transpose and we divide both sides by t. With that being done, we end up with I equals to Q over T. So this is the current. So we have 0.64 coulombs, divided by, let's just put a divided by 0.40 seconds, and that should give us 1.6. I should give us 1.6. Let me refer to my notes. Good. So 1.6 amps. Yep, so we're on the right track right here. 1.6 amps. So that should be it right there. Then it says state the direction in which the charges will flow if the rod is positively charged up through the rod from Earth. So I did a little drawing here. This is my interpretation. Let me know if I'm wrong for this one. This is my interpretation. So you're going to have some sort of separation of charge right here. So you're going to have all the negatives and then the positives down here being repelled. So then these going to move up. If that's my interpretation. I really wish I had a picture for this. But if it's not correct, well, sorry about that. But that's my interpretation. And if I was given this question here, I would have drawn this so they could see that I needed a drawing for this question. Anyway, moving on to things that we understand. Explain how the static buildup of charges on a vehicle could be hazardous. So it says, this could cause a lot of friction between the charged particles, which could eventually cause a spark. And this spark, if it happens while the vehicle is being fueled, could cause an explosion. Okay, so the last question, we are almost done. Yay! It says figure 7 shows the experimental arrangement of the apparatus used to carry out the Rutherford's alpha particle scattering experiment to identify the structure of the atom. A beam, collimated beam of alpha particles from a radioactive source was fired at a thin piece of gold foil, and the angle of deviation of the alpha particles were observed. Now, this is something I would encourage you to look up on YouTube, because they have actual professors that carried this out in modern day, right? And you can see it for yourself so you can remember it, okay? Now it says, write the names of the two scientists who assisted Rutherford in performing this experiment. Could you imagine if you didn't know these names for two stupid marks? Alright, so it was Hans Geiger. You don't have to write the first name. You could have just written Geiger and Marsden if you didn't remember the first name. But it's Hans Geiger and Ernest Marsden. 2 marks. Oh my god. Wow. Then it says, explain why the experiment was carried out in an evacuated chamber. And it is carried out in an evacuated chamber because alpha particles are stopped by just a few centimeters of air. Alpha particles kind of sensitive. So like I was saying, most of this test was kind of theory, coming from question 4 right down to 6. So read, because remember one year they asked, nearly every question was, what is the principle of this? What is the law of this? So learn your laws, learn your principles. So it says, state the conclusions that were deduced from each of the following observations made from the alpha particle scattering experiment. So it says, most of the alpha particles pass through the gold foil undeviated. But this happened because most of the atom is made up of empty space. Well, most of the atoms that make up, the gold foil, they're made up of empty space through which alpha particles are able to pass through. Then explain a few alpha particles. Well, explain how a few alpha particles were deflected from their path but continued through the gold foil. Well, it's like when you're walking on a busy street and you have to go around people, so that's what happened. They came close to the nucleus but didn't hit it head on. So they hit the sides of the nucleus, and so they were slightly deflected from the original path. Now, some were totally rebounded. They were hit away. And this is because these are the particles that actually hit the nucleus head on. The nucleus of the gold atoms head on. And since the nucleus and alpha particles are positive, they were repelled and rebounded. Alright, so it says, describe the Rutherford model of the atom based on the conclusion of the experiment stated in B. Most of the atom is made up of empty space. That's what he showed. And the nucleus is extremely dense and consists of positive charges which repel the positively charged alpha particles which hit the nucleus head on. Students, make sure you read all the scientists in atom, physics of the atom, that chapter, because sometimes they don't ask these in-depth questions. Okay, so now we're saying energy is produced within stars by a process called nuclear fusion, where alpha particles help convert beryllium into carbon according to the equation below. That's not the one you would see in books. You would usually see just two hydrogen nuclei just attacking each other, but they use this one, which is cool. In the equation above, which symbol is used to represent the alpha particle? Remember, you usually write it as He42. So the actual symbol only, so you just write He, which is the helium. Yay. Then it says the following table shows the mass of each nuclei in the process above. So now we get into Einstein's big discovery, where he related energy to mass, and basically was like energy is mass. So now we have here all the weights, the masses of these particles here: helium, beryllium, a neutron, and a carbon atom. Okay, and 1 U is equal to 1.66 10 to negative 27 kilograms. Okay, so how to calculate the loss in mass? You always minus the before, always minus the after from the before, and you could do it without multiplying all of these. So your calculation will be fast and clean, and would have less problems. Like you meet less, less mistakes. So I added up the before. The before was helium and beryllium, and there were no extra molecules. It was just them. So I looked for their masses and I added them, and I got this right here. And then I did the same thing for a neutron and a carbon atom, and this is the mass I got here. Subtracted the before from the after. Subtracted the after from the before. So mass before minus mass after, and I got 0.00605 U. And whatever answer I got, I converted it, because and I multiplied by 1.66 times 10 to the negative 27 kilograms. Because if 1 U is equal to 1.66 times 10 to the negative 27, then 0.00605 U will equal to X. You just transpose, so this go here, this go there, this go there, and then you get this. And so the answer is 1.0043 times 10 to the negative 29 kilograms. That's the answer right there for that. So once you work out your delta M, the asks calculate the energy equivalence of the mass in D2. And they gave us the speed of light as being 3 times 10 to the 8 meters per second. So please remember to square the speed of light using your answer and putting in your units. Never forget your units. You stick them in there, and I got 9.0387 times 10 to the negative 13 joules. So just note that kg m squared over S to the fourth. So basically this is kg times m over s. So I put the wrong units, my bad. That's where I paused, so this should be -1 and -1. That's where I paused. So this would be, this unit kg m squared over s squared would be equivalent to a joule. That's the end of this paper. So if you see any discrepancies, let me know in the comments down below, or shoot me up. I would always answer. And remember, we are perfectly imperfect. We are not without imperfections, which makes us great and perfect in every way. So let me know if you got the same answers, and I hope I was able to help you. It has been a very long time since I've come online, and that was because I've had to deal with life a bit. So I would apologize for that, but I really hope I did help you. Alright, see you later. Hope you enjoy. Bye.